about is limits, and these are fairly intuitive. Essentially, a limit is just where the graph, if you look at it visually, it's where the graph goes to on this coordinate plane. So, let me do less explaining and let's just actually try some of these problems right here. So, in this problem, the first three are actually not asking about limits. They're just asking about, what the value of the function f is at certain points. So using this graph, we can see, f of 0 over here, we can see is undefined because there's no black point, no black line where x equals 0. And so that means that the function is not defined there. So f of 0 is undefined. And the next question is f of 2. And we can see here f of 2 is 0 from this graph. So we can write that. And f of 3 similarly. Now, if you look here, there are a bunch of these discontinuities at x equals 3. There are a bunch of these holes, but those are not actually the value of f of 3. The real value of f of 3 is this black point here, which signals the point where the function f is actually defined. And so from that point, we can see that f of 3 equals 3. Okay, so we're going to write that. And next we're going to get into limits. So I'm going to explain this. This right here is a limit, LIM, and sometimes you'll have left and right hand limits. So this negative sign, what it means is that it's asking for the limit as x approaches 0 from the left. Left because the negative is on the left side of the x-axis. So as x approaches 0 from the left, we can see here f of x goes to negative infinity. So that would be the answer here. It would be negative infinity. And for the next problem, the limit as x goes to 0, just in general, notice how there's no negative or positive of f of x. Now this, we would say, is undefined because this limit does not exist if the left and right hand limits are not equal. And from part D, we have the limit as x approaches 0 from the left is negative infinity. But if we look at the graph, the limit as x approaches 0 from the right is actually 2. And negative infinity is not equal to 2, and therefore this limit does not exist. So we often put D and E as a abbreviation for it does not exist, so I'm just going to put that. Okay, the next one. Now again, this is a right hand limit. This is the limit as x approaches 3 from the right of f of x, and we can see here as x approaches 3 from the right, we can see the limit f of x approaches the value 2. And so the answer to this would be 2. And looking at G, the limit as x approaches 3 of f of x. Now, once again, this limit does not exist, and that is because the left and right limits are not equal. And you can see as x approaches 3 from the left side, the limit f of x approaches 1, whereas if you approach x equals 3 from the right side, f of x approaches 2, and 1 is not equal to 2. So G would be does not exist. Okay, and for the last question, the limit as x approaches negative infinity of f of x. So we can look here, just, graphically, visually, looking at it as x approaches negative infinity. So that's as x goes to this side. We can see this here, this dot, this line is called a horizontal asymptote, and we this line, if you can extend it to the y-axis, goes to 1. So, the answer to this question would be 1. Okay, now I want to go and talk about some limit properties. And there are some properties of limits that are pretty important to know. So I'm going to start by setting everything up, okay? And I'm going to write everything out. I'm going to write out a couple of conditions, basically. So if L, M, C, and K are all real numbers, I'm just going to put belongs to this set of real numbers. If they are all real numbers, oh, my pen. Sometimes my pen is a little, it sometimes doesn't work, but that's okay. Okay, L, M, C, K are real numbers, and limit as x approaches C of f of x equals L, while the limit as x approaches C of g of x equals M. Then, if this is true, we have a couple of properties. So, the first one is the sum rule. Okay, so this is pretty intuitive. And what it basically says is, oh, okay, my pen. I'm going to change to a different color. What it basically says is the limit as x approaches C of f of x plus g of x equals the limit as x approaches C of f of x, plus the limit as x approaches C of g of x equals L plus M. So this is a pretty intuitive property, but this is the sum rule. People don't usually refer to it as that, but it is still something that you need to know. And similarly, there is the difference rule, which is quite literally the same thing. So I'm going to not write everything out this time. So that we have the difference rule. And what that says is the limit as x approaches C of f of x minus g of x is just L minus M. That's all that says. And following this trend of using all the, arithmetic operations, we have the product rule. Okay, so the product rule. What this basically says, it's very intuitive as well. The limit as x approaches C of f of x. Sorry, that's little. Let me redo that. F of x times g of x equals L times M. Okay, that's the product rule. And then we also have something called a constant multiple rule. Okay, constant multiple rule. Actually, I'm going to start a new page because I've run out of space. Okay, we have the constant multiple rule. Let me write what did I just do? Okay, constant. Let me zoom in a little bit. Multiple rule. And what this basically says is, suppose we have k is a constant, so we've defined that before. We have k right here is a constant, okay? And given that k is a constant, we have the limit as x approaches C of k times f of x is equal to k times the limit as x approaches C of f of x, which is equal to k times L. Okay, so that is the constant multiple rule. And the next rule is the quotient rule. which again, pretty intuitive. Quotient rule. Oh, I don't know what happened there. So the quotient rule basically states that the limit as x approaches c of f of x over g of x equals the limit as x approaches c of f of x over the limit as x approaches c of g of x equals, equals L over M. And there is a very crucial rule that we have to keep in mind here, specifically for the quotient rule, and that rule is that M cannot be 0. Okay, because M is on the bottom of the fraction, M is the denominator of this fraction, and if M was 0, then this whole value would be undefined. Okay, so we need M is not equal to 0. Okay, and lastly, we also have the power rule. So, power rule. What the power rule states is that the limit as x approaches c for f of x to the power of r over s is equal to L to the power of r over s, given that, let me write in blue, okay, given that r and s are integers. I'm just gonna write r belong to the set of integers, and we need L greater than 0 if s is even. Okay, because when you consider the negatives and everything, it gets really messy. But for the most part, this power rule is pretty intuitive as well. Okay, now I want to get into the next big topic, which is continuity. So, and you might have heard this, this word tossed around a lot. It is a very important word in calculus. It's used in a lot of definitions. It's used in a lot of theorems as a requirement for a function to be continuous. And so let's look at what that really means. So the official definition of continuity, okay, we have, let me write this definition. Okay, we have, so there are like 3 requirements for a function to be continuous at point x equals a. The first is we need f of x to be defined at x equals a. So f of x is defined, oh my god, okay, defined at x equals a. That's the first condition. The second condition is we need the limit of, as x approaches a, of f of x exists. Okay, so the limit has to exist. This means the right and left hand limit. So as x approaches a from the right and left, it has to approach the same value. And then the third condition, and this is the very important one that makes this whole function f continuous, we need f of a is equal to the limit as x goes to a of f of x. Okay, so the function is defined at x equals a, and whatever value it's defined as is equal to the limit. Okay, and so this is basically the official definition of, of continuity. And if all of these requirements are met, then we can say that f of x is continuous at point a, x equals a. Okay, so that's the definition of continuity. And you might ask now for endpoints of a function, okay, because sometimes a function has defined endpoints. It'll look like this or something. For endpoints, how do we tell if endpoints are continuous? this is a function f of x. F of x would be continuous at point B if, first of all, f of b exists, okay? And, based on this graph, we can tell it does exist. And also the limit as x approaches b of f of x is equal to the value of f of b, okay? And the limit as x approaches b from the left is equal to f of b. So then, if that condition is met, then the function is continuous at x equals b. So, to summarize the whole thing, basically, for endpoints, we just need to use the left and right hand limits. So use left and right hand limits. Okay, that is the definition of continuity. Okay, and now I want to just quickly talk about some types of discontinuities. Okay, there are 4 main types of discontinuities. Discontinuities as in when a function is not continuous. Okay, the first one is what we would call a removable discontinuity or a hole. So, removable discontinuity slash hole. And this would be if the function looks something like this. Okay, this hole right here is a removable discontinuity because essentially it's like you just removed a point from the graph. Like, let's say this is 1 at x equals 1, you just removed f of x from the graph. It's defined at every other point. It's just this, literally, it's like a hole. So very intuitive. That's what a removable discontinuity is. The second type of discontinuity is a jump. Okay, I'm not going to write discontinuity, but a jump discontinuity is essentially something like this. Let's say this is x equals 1. It would be like this. Okay, notice, I'm sorry, there has to be an open circle there. Notice how the function is defined at x equals 1. However, the left and right hand limits as x approaches 1 are not equal. Here it's at this value, whereas, if you approach x equals 1 from the right side, it's at a different value. And so the limit does not exist, and therefore the limit cannot equal the value of the function at x equals 1. And so this is what we would call a jump discontinuity. Again, pretty intuitive, literally like a jump. Okay, next what we have is a infinite discontinuity. Okay, and this, really, when you think of infinite, just think infinity. Okay, so this would be something like, let's say this is x equals 1. It would be if a graph is like this, and there's like a vertical asymptote here. Okay, so as x approaches 1, and you can have 1 on this side too, as x approaches 1 from either side, f of x approaches infinity. Okay, and you would call that a infinite discontinuity. Okay, and the last type of discontinuity I want to talk about is an oscillating discontinuity. Oscillating. Okay, and this happens in very specific instances, but the most famous one, which I will just talk about really quickly, is the graph of sine of 1 over x. And this graph, essentially, what it looks like is, it looks like this kind of, and as you get closer to 0, the graph oscillates like infinitely between 1, which is here, and -1. So something like that. Okay, that's not a very accurate picture, but that is kind of what the graph looks like. And essentially what you can see here is the limit as x approaches 0 of is about continuity in general, thinking about it graphically, is that if you just think about it visually, if you just think about what it looks like on the graph, a discontinuity occurs when you have to lift up your pen from the paper. Okay, so on a graph, if you are able to draw a function without lifting up your pen at all, like that, for example, I don't know what kind of function that is, but it is a function. If I didn't lift up my pen at all, this function is continuous on its domain. Whereas, if I have a function like this, and I have, let's say there's a removable discontinuity there, I'm gonna have to pick up my pen to draw this function, because I can't just keep tracing the function through this point right here, because this point is undefined. I have to stop and then start again. So, graphically / visually, that's what a discontinuity is. It's when you have to lift up your pen from the paper. Okay, one application of continuity I want to talk about is this theorem called the, let me use black actually. It is called the intermediate value theorem. Excuse me. Okay. Intermediate value theorem. And it's also abbreviated as the IVT. And this is one of those theorems that, like I mentioned earlier, uses continuity as a requirement for the theorem to work. So, it states that if you have a function f, okay, f of x, that is continuous, I can't spell continuous, is continuous on the interval, the closed interval, a to b, okay, and you have a condition that, let me go on to the next line, if f of x is continuous on a to b, and f of a is less than m is less than f of b for some m, okay? My thing is not cooperating, for some m, okay, then there must exist a c, okay, c is another value. A value c, where c c belongs to the interval of a comma b. Okay, so c is between a and b, such that f of c equals m. Okay, so let's look and read that all over again. If f of x is continuous on the closed interval of a to b, and f of a is less than f of b for some m, then there must exist a value c where c belongs to the open interval of a comma b, such that f of c equals m. Okay, and it's a very wordy definition, but what it essentially means is, say f, let me draw a quick diagram. Say this is a, this is b. Say f, this is f. It's just a random continuous function, f of x. Okay, and it's continuous on the closed interval of a comma b. Okay, and let's say there is this point m. Let's say this is m. Okay. There's a point m such that m is between f of a and f of b. Oh, actually that's a little close. Let me draw a better map. Okay, we're gonna say here there is a point m here, okay, such that m is less than f of b, okay, and it's greater than f of a. Then there must exist a value c, where c is between a and b, such that f of c equals m. So basically, where did those dots come from? What are those? Okay. Basically, if we extend this line m, we can see there are actually multiple C's. In this case, there are multiple cases, but you can tell that there are points, you know, there are values of x between a and b such that f of x is equal to m. Okay. Oh, didn't mean to delete that. Yeah. So this is the intermediate value theorem. It's, again, the definition really complicated, but if you think about it, it's really, really intuitive. It's basically just saying, you know, if you have a function, if you have a function, like the function is going to hit every point between these two. If you have a function but in a closed interval, then the function is going to hit every value between the value of the function at those endpoints. Okay, so essentially, like, you can tell it's continuous, right? You can't lift up your pen, and so the function, there has to be a x value such that the function itself, like f of x, is equal to all the numbers between f of x, f of a, and f of b. That's the intermediate value theorem. Okay, it's a really important theorem to know how to apply. Okay, I'm going to add one more. Oh, actually, I think I have another page here. Okay, yes, perfect. And I want to go over one last thing, which is I want to talk about a couple of really important limits to know and memorize in calculus. So, I'm writing the wrong thing. Important limits. Okay, important limits to know. Okay, perfect. The first one is E. You guys might have heard of E. You know, there are a couple irrational numbers like pi, there's E. But essentially what E is a limit, okay? It's the value of a limit. And specifically, E is the limit as x approaches infinity of 1 plus 1 over x to the power of x. Okay, that is equal to E. Okay, that's literally like the definition of E, at least that I was taught. And as you can tell, it has a lot of important applications and things like compound interest and stuff. You can tell based on just the format of this function. The second limit I want to talk about is the limit as x approaches 0 of sine x over x. And this limit is equal to 1. There are a couple ways you can prove this. I'm not going to get into that right now, but either way, this is an important limit to remember. And finally, the third limit is the limit, again, as x approaches 0, of 1 minus cosine x over x is equal to 0. Okay? Limit as x goes to 0 of 1 minus cosine x over x is equal to 0. Again, I'm not going to prove that now. There are proofs if you want to look at them online. But, you know, these are just things that are really important to memorize for any calc exam, okay? They're what I memorized for my AP Calc BC exam, in fact. So, with that, that is the end of this video. I hope you learned something. Maybe this was review for you, maybe it was completely new. I'm really glad to be teaching you all calculus via ASMR. I just took the AP Calc exam this May, and, you know, I feel like I did pretty well. Hopefully I got a 5, but now I want to impart that knowledge on you all. So with that, I hope you enjoyed this video. You know, look forward to the next one, and thank you for watching.